Hello friends, welcome to this second video on operation on set theory. Normally, what do we mean by operation? When there are going to be a collection of elements, if you want to further do some calculation based on them, then we will need some operators which can operate on them and give us an output for us. Like basic operations for mathematics can be stated as addition, subtraction, multiplication, division and so on. They act on numbers and they are going to produce outcomes which are desired results. In set theory, what we have is going to be a collection of objects. So whenever we have objects which are not going to be number, which can be something like a lion, cat, tiger and so on, or it can be pink, red, yellow and colors and so on. So whenever they are going to be non-numerical, how to operate on them. So we will see on operators which can operate on your set theory. Okay, so we move on to the next thing to get introduced to the basic operations which are available in set theory. Let U be the universal set, and if A is going to be any set and B is also going to be any set out of it, then we read A union B to be A union B. This symbol with U sign is going to be union B, is containing all elements that are going to be in A or in B. So it is something like your OR operator which we use in our logic gates, either A or in B, or it can be in both. So how do we denote them? By our set builder notation, A union B is going to be equal to set of all x such that x either belongs to A or it belongs to B. Next is the symbol with an ulta pulta of U like an N. You call it as A intersection B. So what does this intersection mean to us? It contains all elements that belong to both A and B. So it is nothing but just our AND operator which we use in our logic gates, A and B. So only if both of them are on, then there will be an output over here. So we call this to be intersection operator. You denote it as set of all x such that x belongs to A and x belongs to B. The next thing which we have over here is A to the power of C, or A with an prime on top, or A with a bar on top. You call it as complement of A, which are nothing but collection of all elements which are going to be not in A. So they are a part of the universal set, but they don't belong to the set A, in which case you call them to be complement of A. Two sets A and B are called disjoint if they have no element in common. So if they are not going to have any element in common, what they are referred as disjoint. So what will be the number of elements which is going to be contained both A and B? If they are disjoint, there are going to be no elements in common, so intersection will be empty. So this is a condition for disjointness. A intersection B is always empty when the sets are going to be disjoint. Now we will see how these things work using some numerical examples so that we will get to know about these operators in a better way or better understanding. The easy way to grasp all these things are using some pictorial representation, and we know that a brain can process fast when it is seeing things as pictures. So we use something called as Venn diagrams to represent these relations. So this universal set, when I usually make use of something like this with a square or a rectangle to represent the collection of all. So this is going to be your universal set. Make sure that you differentiate your universal set with your union symbol so that you don't get confused with it. So if A is going to be a set inside it, then this set is a collection which I am going to denote it by a circle. This collection is going to be A. A is a set and it is going to be a subset of the universal set. So B is going to be one more set. So this is also a subset of your universal set. So A and B are going to be universal sets, subsets. So when I say A and B, A and, sorry, this is going to be A and B. So elements which are common to A as well as elements that are common to B. So how will I write them? So let this be my universal set U, and let me have an A over here. So let this be my A, and let me have my B over here. Let this be my B. I want elements that are going to be both. So this means both for me, both A and B. So where is going to be the part which contains both A and B? So this is going to be the portion that contains both A and B. And when it is going to be A union B, a collection that takes A or B, so how will you represent that by? So you have the same universal set. Let me draw my A and let me have my B. So when I have a A and this is going to be B, elements that are either in A or in B. So either in A, they are going to be part of A. So I take this portion of A. They are also either in B, they are also going to be portion of B. So I can also extend them to include portions of B. So either A or B, A union B, how will this look like? So it is a collection of A and B, both of them. Okay, A or they are going to be a part of B. So this is how we represent union using your Venn diagram, and this is the way in which we represent intersection in our Venn diagram. And moving on to the third one, whenever I am going to have my set, universal set U, and this is going to be my set which is going to be A. So what is the third operator which we saw over here? You call it as complement. Elements that are going to be in your universal set, but they are not going to belong to, does not belong to A. So they are portion of the whole but not in A. So where are they going to lie? They are going to lie away from A. Apart from A, whatever is going to be the collection which I can take from the universal set. So this is what you call it by the name complement. Okay, so you write it either with A with a C on top, or you can write it with A with a prime on top, or you can write A with a bar on top. Okay, what do you call this as? You call this as complement. So this is how we can represent the relationship between sets using pictorially, and we call this by the name called as Venn diagram. So now let us move on to have some problems which can define them. So let A be the set which is going to be the collection 1, 2, 3. Let B be the set, the collection 2, 3, 4. Let me have A union B, collection of elements of A or B. So it can either be in A or in B. So I will take elements of B now. When I take elements of B, 2 is already being over here represented. So don't take it again. So it is a unique collection, like you don't have repetition of objects over here. This 3 and this 3 are the same. So you don't take it twice. Okay. And so the other left out quantity over here in B is going to be 4. So either A or in B. So either A or in B. So the collection will have 1, 2, 3 and 4. When I write it as A intersection B, so A and B, so both it has to be in A as well as in B. So 1 is present here, but it is not present here, so I cannot take 1. 2 is present here, yes, it is also present here, so I will take 2, which is going to be both in A and B. Next 3 is over here and also over here, so I will take it over here. Moving on to the next one, 4, it is in B but not a part of A, so I cannot take it. So the intersection will contain both A and B, will contain 2 elements in common, which is given by 2 and 3. So now if I define my universal set to be, use the collection of 1, 2, 3, 4 and 5. And I have already defined my A to be equal to 1, 2 and 3. What can you say about A complement? A's complement are elements of U but are not in A. So belongs to U, they does not belong to A. So these elements 1, 2, 3 which are going to be in A are going to be slashed off So what is left out is going to be 4 and 5, which are going to be your part of your complement. So this is how this condition or this operator on complement operates. Moving on to the next operators, we have the difference operator, which is going to be read as A difference B, or relative complement of B, of A with B with respect to A. That is nothing but elements which are in A but not in B. So you read it as collection of all x such that x belongs to A, x does not belong to B. So from A you scrap off all the elements of B, whatever is left out then you call them as difference. So let us have the collection A to be 1, 2, 3 and B to be the collection 1, 3, 5, 7. From A I scrap off elements of B. What are the elements of B? 1. Okay, I scrap off 1. Next is going to be 3. I scrap off 3. 5. I don't have a 5. I don't have a 7. So what is left out in A after removing all the elements of B? I just have this 2 over here. So A minus B is going to be 2. And what about B minus A? From B you scrap off elements of A. So B is going to be equal to 1, 3, 5 and 7. And from here you scrap off elements of A. 1 is scored off, 2 is not here, 3 is scored off. So what is left out is going to be 5 and 7. So B minus A is going to be 5 and 7. So what do we say over here using our Venn diagram is, this is going to be my universal set U, and then I have a bigger set which is going to be my B, and from this B I am going to remove my set called as A. So when I am removing this A from my B, what will be left out for me? The left out portion is going to be this one over here, like a donut. So this yellow portion represents B from which A has been removed, B minus A. Okay, so this is going to be your B minus A. When I want it to be A minus B, how will I represent this as? When it is A minus B, the bigger set is going to be your A and the smaller one is going to be your B. And when you remove elements of B from A, you will have this left out portion over here. So this is the portion. This is nothing that represents A minus B. Okay, next we move on to the last one called as symmetric difference. What is meant by symmetric difference? It is going to be a combination of A minus B and B minus A, and then you take the union of both of them. So you write it with a symbol plus and then encircle it. So it is a combination of both A minus B and B minus A. Collection of elements, either they are in A minus B or in B minus A. So let us have an example. A is going to be the set A, B, C, D and B is C, D, E, F. What can we say about A minus B? From my A, B, C, D, I am removing B. C is there, yes, C is removed. D is there, D is removed. E is not there, F is not there. So my A minus B is going to be A comma B. Now from my B, which is C, D, E, F, I am going to remove my A. So I want B minus A. So what is A? A is here. No, I don't have a A. B, no B. C is removed. D is removed. What is left out is going to be E and F. Now I have a minus B and I also have a B minus A. I take the union of both of them. So my A plus circle B, you call it as symmetric difference B, is going to be the collection A comma B comma E comma F. So this is the union, the collection either in A minus B or in B minus A, which is represented in this way. So how do we denote this in a pictorial way? So using your Venn diagram, let this be your universal set and let us have a set called as A, and this is going to be my set called as B. So this is my B, A minus B. From A you remove the part of B. So when you from A you remove the part of B, what are the left out portions? This is my left out portion. And similarly from B, when you remove the parts of A, what is the quantity left out? This is the left out. So this portion shaded part is nothing but your asymmetric difference B. So in this way we can represent the set using pictorial way called as Venn diagram, and this is how helps Venn diagrams helps us to identify or visualize how the collection is going to be, and we can effectively apply these operators to perform operations on the given sets. Thank you very much.